Good evening. I'm Dick Meserve, the president of the Carnegie Institution, and I'd like to welcome you all to a Capital Science Evening. This is a special event this evening in many respects. We are hosting tonight's event jointly with the Australian Embassy. And to get us started, I'd like to invite Ambassador Beasley from the Australian Ambassador to the United States to join me at the podium and to provide a few words of greeting.
Well, thank you very much, Dr. Meserve. And ladies and gentlemen, it's a privilege and a pleasure to be here tonight. And thank you in particular to the Carnegie Institution for Science for hosting this terrific lecture series. Well, on behalf of the Australian Government, the Australian National University and Australian Astronomy Limited, I want to welcome you to what will no doubt be a completely inspiring lecture from one of Australia's greatest and most inspiring scientists, Professor Brian Schmidt. Brian Schmidt has certainly made a mark on his adopted homeland. He landed in our capital city, Canberra, in 1994 with a freshly minted PhD from Harvard and degrees in astronomy and physics from the University of Arizona. Lured, he says, by the chance to be involved in research that would be memorable. He wanted to do research that looked at the big questions and decided that Mount Stromlo Observatory at the Australian National University was just the place for a young researcher to do that. Leading a team of 20 and working with Adam Rice at Johns Hopkins University, Professor Schmidt set out to use light from a supernova, one so distant that it had taken billions of years to reach us, to figure out the rate at which the universe was slowing down over time. But the results the team got indicated something totally different. Something that Professor Schmidt says he first thought was a mistake. They and another team, led by joint Nobel Laureate, Professor Saul Perlmutter, discovered the universe was actually speeding up. They had, as a result, made, as it turns out, the discovery of the decade. And Professor Schmidt's gambit of moving to the other side of the world to do memorable research certainly paid off, and we do claim him, and you've got to understand that. But we're very generous at sharing people. With an auspicious start like that, it isn't surprising that Professor Schmidt has won numerous national and international awards throughout his career. Late last year, he became the first Australian to be awarded the Nobel Prize for Physics since 1915. To say he's brought honour to his adopted homeland would be an understatement. He has done all of this while continuing to be an outstanding educator and engaged member of our community. On the day he found out he would be sharing a Nobel Prize with Professors Rice and Perlmutter, he took uncountable calls, including, and this as befits his dual status, one from the White House, and met with our Prime Minister, Julia Gillard. He did 30 media interviews, which suggests to me that since I've left the ANU, their press section is out of control. And at the same time taught his third-year undergraduate cosmology class. That must have been the most memorable class for the young students that day. Admittedly, his lesson plan for that day was altered somewhat. He has also made his mark as a philanthropist and has most recently generously contributed $100,000 of his prize money to support the Australian Academy of Sciences Primary Connections program, which links literacy with science in primary and secondary schools across Australia. That's not very surprising to an American audience. Americans are the most generous people on earth. That is objectively the case. They are generous unbelievably with their own money. We are not. That is, we do believe very firmly that the government and via the government, the collective community has some certain responsibilities. And those responsibilities will be performed via the taxation system, and that's the only contributing we're going to do. So that's a big difference. So for somebody to give up, an academic, and they get paid virtually nothing in Australia, to give up 100,000 is a truly extraordinary, generous thing to have done. He continues too an impressive research career, currently leading the Sky Mapper project, which is conducting the first full digital survey of the southern skies. It is a project that Professor Schmidt has described as making, quote, a treasure map to hunt down the interesting things in the sky, such as the first stars created after the Big Bang, the first black holes created after the Big Bang, and the planets that exist like Pluto, dwarf planets. Professor is also heavily involved in the Giant Magellan Telescope, which Australia, through the Australian National University and Australian Astronomy Limited, is proud to be a foundation partner with our friends here at Carnegie. The GMT is a product of more than a century of astronomical research and telescope building by some of the world's leading research institutions. It will open a new window on the universe for the 21st century. Scheduled for completion around 2018, the GMT will have the revolving power of a 24.5 metre, 80-foot primary mirror, far larger than any other telescope ever built. It will answer many of the questions at the forefront of astrophysics today, and will pose new and unanticipated riddles for future generations of astronomers. The Australian government has committed nearly $90 million to this project because it will do important science. It will be the premier optical infrared facility for our astronomers. Being part of the consortium building the telescope will keep Australia at the forefront of optical astronomy, and will help us to continue to attract to our shores immensely talented scientists like Professor Schmidt. I hope you will all enjoy looking at and thinking about our universe this evening with our great professor.
Thank you, Mr. Ambassador. It is really wonderful to have the Australians as our partner in this effort to build the Giant Magellan Telescope. If you search for online photos of Albert Einstein, you will find an image of Einstein peering into the eyepiece of the Carnegie Institution's 100-inch telescope on Mount Wilson. Behind him, smoking a pipe and with a wrinkled brow, you see Carnegie astronomer Edwin Hubble. The photo was taken in 1931. Only 2 years before, Hubble had published a paper showing a linear relationship between velocity and the distance of faraway galaxies. The surprising conclusion from his work was that the universe was expanding. This conclusion was surprising because virtually all theorists at the time, including Einstein, believed the universe to be static. It is tempting to think that Einstein, who I bet had never looked through a telescope eyepiece before, that he had come to Mount Wilson to check up on Hubble, to make sure he hadn't made any mistakes. Hubble's observation had invalidated a part of Einstein's equations of general relativity. They had made unnecessary a term called the cosmological constant that Einstein had slipped into his equations in order for them to be consistent with an assumed static universe. Without it, his equations predicted that gravity would make the universe collapse. During his 1931 visit to Mount Wilson, Einstein declared that Hubble's observations smashed my old construction like a hammer blow. He famously said that his greatest blunder was the introduction of the cosmological constant into his equations. Einstein's dismay might have been premature. In the late 1990s, as Ambassador Beasley has indicated, two teams of cosmologists, astronomers, one of them led by our guest tonight, Dr. Brian Schmidt, used distant exploding stars called type 1a supernovae to discover that the expansion of the universe is accelerating. That is, the universe is expanding faster and faster over time. This was surprising because astronomers have assumed that gravity would ultimately cause the expansion to slow down. The result is very strange. What could this anti-gravity force be that is pushing the galaxies apart? There was nothing in the physics toolbox outside of Einstein's cosmological constant that could begin to explain it, and of course it may not be the answer. Even today, dark energy, the term astronomers now use to explain the acceleration of the universe, remains one of the biggest puzzles in physics. Along with dark matter, a mysterious type of matter discovered in 1980, a discovery, I might add, in which Carnegie astronomer Vera Rubin played a major role. Dark energy has the capacity to overturn our understanding of physical laws. At the very least, the double enigmas of dark energy and dark matter have changed how we think about the universe. Brian Schmidt was born in Montana and raised in Montana and Alaska. He received his bachelor's degree from the University of Arizona and his master's and PhD from Harvard. He was a fellow at the Harvard-Smithsonian Center for Astrophysics when in 1994 he formed the High-Redshift Supernova Search Team. Another member of that team was Mark Phillips, now serving as Associate Director of Carnegie's Las Campanas Observatory in Chile, and former Carnegie Fellow Nicholas Suntzeff. The team's discovery of the accelerated expansion of the universe was named Science Magazine's Breakthrough of the Year in 1998. And last year, as you know, it earned a Nobel Prize for Dr. Schmidt. Shortly after forming his search team, Dr. Schmidt moved to Australia, where I understand his wife is an Australian. And he became a laureate fellow at the Australian National University's Mount Stromlo University near Canberra. When he is not doing science, he makes wine, producing Pinot Noir in his small winery. The Nobel Prize caps a long string of awards for Dr. Schmidt. This include the Australian government's inaugural Malcolm McIntosh Award for Achievement in the Physical Sciences in 2000, the Australian Academy of Sciences Posey Medal in 2001, and the Astronomical Society of India's Vainu Bapu Gold Medal in 2002. Then in 2006, he was awarded a Shaw Prize for Astronomy, and in 2007, he and his team shared the 2007 Gruber Prize for Cosmology. Dr. Schmidt is a fellow of both the Australian Academy of Science and the U.S. National Academy of Sciences. Dr. Schmidt joins a long list of distinguished colleagues, including Albert Einstein and Edwin Hubble, who have helped us understand the strange and wonderful universe that we inhabit. Ladies and gentlemen, please give a warm welcome to Dr. Brian Schmidt. Good luck.
Thank you, everyone. I want to make sure my microphone's working good. Working too well. Anyway, thank you all for coming out tonight. It's my pleasure to be able to tell you about the universe from beginning to end. Now, in doing that, I'm going to probably try to explain to you what was in the introductions, because that is essentially part of the story. So, to start things off, I realize not all of us spend our time looking at the skies, and I want to give you a quick tour through the universe. And that universe, we're going to use a ruler, which is a little different than normal, than the one, it's not in centimeters or it's not in inches. It's going to be the rate that light travels through space. So light travels 300,000 kilometers or 186,000 miles per second. And that means that it can go around the Earth 7.5 times in a second. Now that's fast, but it's not infinitely fast. And so, since the cosmos are so large, we're going to use that as the way to judge our distances, and we're going to put it in terms of time rather than in our normal meters. So let's just start off with, for example, the Earth-Moon system. That's about 1.5 light seconds. So when Neil Armstrong said his famous words, it took 1.5 light seconds to bounce to a radio receiver just outside where I live now in Canberra, and eventually beamed back here to the US public. But it was 1.5 seconds after he said his famous words. If you go and look at the sun, it's a lot bigger than you may realize. It's 5 light seconds across. I think most of us know that if you go from the Earth to the sun, it's 8 light minutes. That's one of the things they told us in school. But you may not realize that our solar system is about 10 light hours in size. So when you go out to, for example, Pluto, which used to be a planet and now has been demoted to a dwarf planet, I will say that I was one of the people who voted against Pluto's demotion. Yes. Not based on any scientific purpose, but my view is once you're a planet, you're always a planet. It's just part of the deal. So if you ever come down to Australia, you'll go out and you will see the Southern Cross, assuming you go someplace other than Sydney, and you'll see one of the brightest stars in the sky, Alpha Centauri, 4.3 light years in distance. Now, Alpha Centauri is a star not dissimilar to our own sun, very similar in size. And so if Alpha Centauri were a pea, for example, then our sun would be located roughly at New York City in distance, with everything else in between space. So 2 peas, 200 miles apart. That is how big space is. Particularly remarkable when you think that our own galaxy is full of 10 billion stars. It's one of the fanciest and most exciting places in the universe, and we're located some 30,000 light years from the center. Now, that's sort of what the Milky Way looks like when you look up, at least from Australia, where the center of the galaxy goes overhead each night. But if you were to look at it from above, then it's sort of a pinwheel, and we see it depending on whether or not you're inside it. It looks like that egg, or 2 eggs upside down. If you were to be outside, then it's this sort of interesting, intricate spiral of gas and dust. All right, if we go out to the local neighborhood, what we call the local group, you can go out and you can see the nearest other galaxies. In the southern hemisphere, we have the large and small Magellanic Clouds, which are small galaxies, only billions of stars rather than tens or hundreds of billions of stars. And here in the northern hemisphere, we can look out and we can see the largest nearby galaxy, the Andromeda Galaxy, a galaxy that's slightly bigger than our own, but is located some 2 million years away. That's the nearest part of the universe. In Australia, we made a map, the first comprehensive map of the sky out to about 1 billion light years in distance. And you can see the universe, each dot, there's 221,000 on this diagram, is a galaxy of 100 billion stars. And they form sort of this foam through the cosmos. And so you can see that we are just right in the center of us. There's a lot of stuff out there. Looking even further, we could use the Hubble Space Telescope and look back roughly 12 billion years into the universe's past. We look very, very far away, and light takes time to reach us. And this is an image taken, the deepest image that we've yet taken of the cosmos, the ultra-deep field, as we call it. And the smallest smudges here on this are roughly 12 billion years in the past. So almost 8 billion years before the Earth was formed. Astronomers love to make bigger and bigger telescopes because they allow us to look further and further away. But we do run into problems. Eventually, we run into the end of the universe because the universe is only about 13.7 billion years old. Here is a map of the universe, the whole sky glowing in microwaves. This is actually a picture of the universe when it was only 380,000 years old, and the whole universe was as hot as the sun, or slightly cooler, but very close, and it was glowing. And here we see sort of the first things that eventually turned into the stars and galaxies and structures of galaxies that make up the universe we see today. And before that, well, we have the Big Bang. So, in the beginnings of cosmology, I always like to take it back to 2 things that happened. One was done with a telescope, and it was done by this man, Vesto Melvin Slipher, whose family actually gave me a scholarship, and I didn't know who he was. He's now one of my heroes. So what he did is he took the light of galaxies and spread it out into the colors of the rainbow. And so when you spread the light out of colors of a rainbow, you get what we call a spectrum, which has a fingerprint of every atom. So for example, iron has a series of places where it absorbs color in the blue. Sodium has a particular set of orangey yellow lines, which you will notice when you see, for example, lights around airports. Those are sodium lights, and they emit their light in that area. And so we can go through and we can tell, for example, what distant objects are made of by seeing these fingerprints. But what Slipher did was slightly different. He took the spectrum and he noticed that the lines were shifted, almost inevitably, it turns out, to the red. And using something called the Doppler shift, which I think most of us are used to when, for example, a fire truck's coming towards you, the wavelength of the sound is a wave, gets compressed, and that raises the pitch. If, of course, it goes away from you, the wavelength is stretched, and so the pitch is lowered. It works the same with light, except for when you raise light's pitch, then you're actually making light bluer, or if you are having something go away, you're lowering the pitch, you're lengthening the waves, and that makes light redder. And so what he found in 1916 was a cosmic conundrum. Almost all the galaxies that he looked at were moving away from us. Their light was stretched red. And that was kind of a mystery in 1916 because it seemed like we were in a very special place, an unpopular place in the universe that everything was going away from. And that seemed not like it should be. Since the time of Copernicus, we realized we should live in a place that's like what everywhere else sees. And this seemed to violate that idea. So the way we worked on this, and that was done here, as was alluded to by Hubble, was using distances. Now in astronomy, we can't just lay down a ruler and measure distances because our rulers aren't long enough. So we have to be clever, or stupid as physicists often call us, because we can't actually do an experiment properly. So what we try to do is we go through, and for example, if we knew how bright a candle was, as that candle gets further and further away, the candle light becomes dimmer and dimmer. In the same way, a ruler becomes smaller and smaller. And so we can look at how big things look or how bright things appear and judge their distances. And this is what Hubble was able to do using a law that Newton figured out, which is what we call the inverse square law for light. If you take a light bulb and you halve the distance, it becomes 4 times brighter. So by seeing how bright light bulbs are in space, we can judge distances. But the light bulbs are kind of hard. We don't just have calibrated bulbs out there of 100 watts. We have to go out and make it up. And Edwin Hubble was the person who did this. He had access to the best telescope in the world in the 1920s, the Hooker 100-inch telescope run here by Carnegie. And outside of Los Angeles, he was able to use this telescope to look at Slipher's galaxies. And what he found was that by looking at how bright the brightest stars were in these galaxies, he found that the faster the galaxy was moving away by Slipher, the fainter the stars were. And just to show you what his data looks like, his data is nothing crash hot, but he's a famous guy, and our data is not going to be any better later on, so I figure I might as well give you a comparison. Brighter stars, fainter stars. Low redshift, so not much stretching, lots of stretching. And so that relationship, described as the linear relationship between distance and velocity, was what Hubble made him announce that the universe was expanding. And he did it with great aplomb in 1929 and got pretty much instant recognition for the work. Now, to understand why he said this meant that the universe was expanding, let's go through and do a fake version of the universe, just I'll pretend, which thanks to the wonders of my computer, I can magnify by a few %, so I can expand. And now let's look what happens if I overlay these two images. And what do you see? You see, that wasn't supposed to happen. You can see objects nearby have moved only a little bit. The objects that are very distant have moved a lot. The further away you are in an expanding universe, the faster you'll be moving away. And furthermore, if you were to overlay these images in another spot, with the same, I haven't changed anything, I've just moved the point where I'm comparing them, I see the same thing. And so the beautiful thing about an expanding universe is it represents what Hubble saw, and everyone in the universe sees the same thing. Now, it wasn't just Hubble's idea that making a diagram like this that made him think the universe was expanding. We had something else to back it up, and that was Albert Einstein. Now, as alluded to earlier, Albert Einstein had this great thing. In 1905, he came up with the very famous idea of special relativity, E equals mc squared. But to a physicist, his greatest triumph is something known as general relativity, or his equations of gravity. And he started off in 1907 with a very simple idea of acceleration due to moving faster was completely the same as acceleration by gravity, that you can't tell the difference. Now, that doesn't seem like a very profound thing, but it took Einstein 8 years working on nothing but this to sort out what it meant. And when he sorted it out in 1915, he published what we call his equations of general relativity. And these predicted many things. They predicted that space should be curved. It also predicted, when he allowed himself to go out and measure for the first time cosmology. This is a problem when Newton went out and tried to apply his equations of gravity to cosmology, to a universe that goes on for on and on and on. He couldn't do it. His equations couldn't solve that problem. It nearly drove him nuts. For Einstein, he was able to do this for the first time. And his solution nearly drove him nuts. He found out his solutions were dynamic. That is, the universe should be in motion. But we thought the universe was static. And so he invented this stuff that was talked about, known as the cosmological constant. So it was proposed by Einstein to allow the universe to be still. It makes gravity push rather than pull. And it's completely allowed by his equations. It's just not something that has to be there. When it was later realized that the universe was expanding, said, oh, well, maybe it is, that was a mistake, we don't need it, so we'll move on. But for nowadays, what we think of it is we think of it as energy tied to space itself. If you ask, what is an empty space? 20 years ago, I would have said nothing. But if you believe in the cosmological constant, then you need to believe that there actually is something in empty space itself, and that is energy. So, if you think of how Einstein would view the universe, if we're looking at distant objects, we're looking into the past, and the wavelength of light is a wave, as that light travels through the universe, it gets stretched by the expanding universe. So the further the light travels through the expanding universe, the more that light is stretched. And so we get a redshift due to this expansion of the cosmos. So imagine a universe that's expanding. Well, let's run it into reverse and see what the consequence is. Everything gets closer and closer, and eventually everything is on top of everything else. You have the time of the Big Bang. Naturally comes about from thinking about a universe as expanding. The time when everything's on top of everything else. So graphically, imagine that I have two objects separated now by some distance, and I'm going to run the universe in reverse. When I run the universe back in time, they get closer and closer, and this is essentially, this line is Hubble's constant, as we call it. That's how fast the universe is expanding. Now, when we run it back, and we get to the time when the universe was on top of itself, or the time of the Big Bang. So how fast the universe is expanding tells you about how old the universe is, tells you when the universe started. Now, that's an interesting thing. It was what I worked on for my thesis. It turns out that the number I got for my thesis was a value just a little bit larger than in astronomers' unit 70, but that means 14 billion years. And it turns out the person who solved the problem using the Hubble Space Telescope is here in the audience, Wendy Friedman. So she is one of the people who, I guess, I got a check mark where my thesis was said, okay, you got the correct answer, that was good. But I'm afraid she's the one who gets the credit for getting the correct answer. I only get the credit for getting the right answer. There's a little difference there. She's the one who, I think, convinced everyone what the answer was there. So from the rate the universe is expanding, we think the universe is about 14 billion years old. But there's a complication. How fast the universe is expanding only works if the universe doesn't change in speed over time. Now, we know the universe is full of gravity. We're living proof of that. We all have gravity, some of us more than others. And that gravity pulls on everything else in the universe, and that will slow the universal expansion over time. So our diagram really doesn't necessarily look like this. We know if gravity is at work, it's going to have a different trajectory. The universe is going to be slowing down over time. It will be expanding faster here and slower over time as the gravity tugs on the universe. In this case, the universe would not be as old as 14 billion years if there's a lot of gravity. It might only be 9 or 10 billion years old. And so that is an interesting consequence, especially since many people, at least when I was at school, thought the universe was slowing down a lot. And that implied that the universe was probably only 9 or 10 billion years old. And yet we all were pretty sure that the oldest stars in the universe were about 12 billion years old. And so there's a real problem when the oldest things in the universe are older than the universe itself. And so it kind of makes you realize maybe you're not doing something right. Now, a universe which doesn't have anything in it never slows down. It gets bigger and bigger and bigger over time. It goes on forever. It's infinite into the future. It may have a beginning, but it would not have an end. On the other hand, a universe which is slowing down over time, if it has enough stuff in it, it will reach a maximum size, and just like a ball that I throw up in the air, which gravity pulls down and stops and brings back down to Earth, well, you can imagine if you have enough stuff in the universe, that ball, or that universe in this case, will get bigger and bigger, slowing down, stop, and then go into reverse. So where we have the Big Bang in this universe, this one gives you the Gnab-Gib, which is the Big Bang backwards. So it seemed like an interesting question. What is the ultimate fate of the universe? It turns out it brings one other thing, one other question. The amount that the universe is slowing down tells how old we think the universe is from the Hubble constant. It tells us the ultimate fate of the universe. And it also tells us the shape and weight of the universe. And that's because Einstein's theory of gravity tells you that space can be curved. Now, if you have a really heavy universe with lots of stuff in it, then space itself will be curved by all the stuff in it. Space will wrap around onto itself. It's a universe that if I start heading out this direction, given enough time, I'll eventually end up where I started. It wraps onto itself in a fourth dimension. On the other hand, a universe which is light, well, this is a universe that naturally bends away from itself like a saddle. And finally, a universe which is just right, and has just enough stuff, so it neither bends away from itself or onto itself, we say is flat. And that's a universe that more or less behaves like we're used to here on Earth. And so a just right universe is also just right because theorists who try to understand the beginnings of our universe just after the Big Bang predict that the universe should be flat, that it should just have the right amount of stuff in it to be neither bending onto itself or away from itself. So imagine going and doing an experiment. So when I moved to Australia, I decided I wanted to do something big, and I figured measuring the ultimate fate of the universe was about the biggest project I could think of. So I said, okay, why not give it a chance? And so the idea is the following. Imagine for my thesis, I was able to measure how fast the universe was expanding. Now imagine that I would recreate that and look further and further back in time by looking at more and more distant objects. Well, if I can measure the Hubble constant now and then effectively measure the Hubble constant in the universe's past, I can judge the trajectory of the universe. And so imagine a universe that has a lot of stuff in it. It will be expanding faster in the past and will have slowed down. So faster, slowing down. A universe that has almost nothing in it will take this trajectory and not do much. It'll be the same now as it was in the past. And you could imagine a universe which was at a trajectory on that side of the line, gravity would win, and the universe would eventually end in a crunch. On the other side of the line, well, gravity loses, and the universe goes on forever. That was a very clear question to do. We just had to figure out the trajectory in the past. Of course, I hadn't really thought about, in 1994 when I first did this diagram, I didn't have the part of the diagram on the top half where it says accelerating universe, because I really hadn't contemplated the universe speeding up, because there was no obvious way to make it possibly do that. So how are we going to look back in time? Well, we need a standard light bulb. And nature gave us something close to a standard light bulb called a type 1a supernova. So these exploding stars, to understand them, I'm going to give you a brief history of our sun. Our sun, in about 5 billion years, is going to get very big, and probably, if it doesn't destroy the sun, it'll come close to it. And it'll collapse down to a little star we call a white dwarf, about the size of the Earth, but the mass of the sun. Now, if our sun was instead born as a binary system, then that same process happens, but stars are bigger than planets, and they'll survive a star's evolution long enough so that they can start dumping material onto the white dwarf, what was left over from the first star. These things become, when they reach 1.38 times the mass of our sun, giant thermonuclear bombs, the biggest thermonuclear bombs that we know of in the cosmos. They expand at 30% of the speed of light and reach a brightness of about 5 billion times brighter than our sun. And so they are great things. We can see them a long ways away, and they very conveniently explode at this special time when they're about 1.38 times our sun's size. Now, these things were first looked at by Fritz Zwicky using a Schmidt telescope, not named after me or any of my relatives. And he went out and used photographic plates and took a picture of the sky, and then came back a couple weeks and took another picture of the sky, and then used his brain to go through and blink back and forth between the two pictures and to spot these exploding stars. His work, 30 years later, was made to the first Hubble diagram, very much like what I showed you for Edwin Hubble, where we have bright objects and faint objects, and we have low stretch and high stretch. But his diagram goes much, much further away than Hubble's, but still turns out not far enough to go and judge anything much about the universe. Probably only 100 million years into the universe's past. Now, a team in Chile were the ones who were able to really refine this work. And so these guys went out, and it turns out in 1990 used the same technology that Zwicky had used in the 1930s. It wasn't because they were backward, it was because that was still the technology we had in 1990 to do this experiment. Computers and digital cameras were just simply not here yet at the level we needed. So here's one of the machines they put in. Here's Jose Maza from Chile, and he would go take two pictures and blink them back and forth. I was down visiting Chile in 1991 as part of my thesis work, and one of the research assistants, Mario Hamwi, later now a professor, went, and he was very depressed because he wanted to measure what the universe was doing with these exploding stars. And these exploding stars were supposed to be all the same. And he showed me an object, and I'll show you an astronomer's diagram. This is an object showing the exploding star getting brighter and then fading away. But this object, it got bright and fell in brightness faster than any other object he had seen. And the object was a lot fainter than other objects at about the same distance, or redshift. And so he was very depressed. It turned out a couple years later, using data taken from that Chilean experiment, Mark Phillips, who's now here at Carnegie, went through and realized that there was a trend, that objects that explode quickly are fainter on average than those that explode slowly. And we think we understand it, is that these objects turn out, when they explode, make huge amounts of iron. They make a large fraction of the iron in this room will be made by explosions like this. And it turns out that amount of iron that's made affects how these objects look when they explode. And so with that understanding, that team was able to go through and make a new Hubble diagram, which Mario Hamwi visited me and my colleagues at Harvard and showed me this one. Now, we have distance and redshift the other direction here. It doesn't make any difference. But you can see that the points make a really nice tight line now, rather than one with lots of scatter. And it turns out with this diagram, we were able to realize that supernovae could be used to measure distances about 6% in accuracy. Now 6%, if you're trying to, for example, do your physics exam, is probably not going to get you an A. But for an astronomer who's used to probably doing things to a factor of 2, it was really good. And so it was really empowering, this data. They went, eventually found 29 of these things, which really provide the fundamental basis of using supernovae as accurate distance indicators. The other thing that happened was the technology to find the distant objects became available. An astronomer at Berkeley, Saul Perlmutter, had been working since 1988 to discover distant supernovae, and he had been having a hard time of it. In 1994, he called up Bob Kirshner, my PhD supervisor at Harvard, and said, I have an object for you to look at. Now, he had done this before, and we had looked at things, as had many other astronomers around the world, and we had never really found anything that looked very interesting. And this time, though, when we took the spectrum, and I got it faxed to me the next morning, it looked like one of these exploding stars, but 4 billion years into the universe's past. So that was very exciting. It was even more excited when a couple days later he said, oh, and we have 6 more of these as well. So for 6 years, he hadn't found any, and suddenly he found 7 of them in a period of about 3 months. The technology and the techniques to find these things had finally arrived. So we talked, and we realized very soon that the guys who were learning how to use supernovae to measure accurate distances and the guys who were actually finding them had sort of different ways of approaching the problem. And so we decided that maybe it wasn't going to be possible to work together as much as we might like. And so we ended up founding 2 teams. In our case, I was down in Chile in 1994 talking to Nick Sunsef, who was down at Cerro at the time, and we concocted a new experiment to go out and to essentially measure what the universe was doing back in time. We wanted to measure how much the universe was slowing down. We put in our first proposal, and soon quite a big rivalry was born between these 2 teams, one by Saul Perlmutter, one by me, but we were really representing a whole group of people, about 20 people on either side. Now, this was not easy. The thing that Saul had learned to do was to discover distant objects. And I will say I underestimated how hard it was to find these things. Here is an image taken from the mid-1990s. There's about 5,000 galaxies on it. Now, what we have to do is to find the exploding star. Now, these things are really bright, but they're really far away. So those 2 things mean they're not easy to find. They're pretty faint. But the other thing is supernovae are really rare. In a galaxy of 100 million stars, they only happen, 100 billion stars, they only happen once every 250 years. So you got to look at a lot of galaxies to find one. So in here, just to show you where the object is, in case you didn't see it yourself, it's right there. And the way we figured this out is by not taking 1 image, but taking 2 images. So we're able to go through and digitally manipulate this data, to go through and find the objects. Now, in 1995, we were taking data at a prodigious rate at the time. We were taking 50 gigabytes of data a night. Now, that's not a lot of, that's a Blu-ray DVD now. But our hard drives at the time were only a gigabyte, and our computers were a lot slower than my iPhone. And so trying to make this work on a budget of $8,000, that's how much we had to discover the accelerating universe, it turns out, was $8,000, which was plenty. It was hard. It caused a lot of stress. So we had 3 things that really made this possible, which were new telescopes. That was, for example, the Keck telescopes allowed us to really look and spread the light out of these things and figure out their redshifts. It really was not possible before 1995 to do this. The telescopes simply were not big enough. We had the Hubble Space Telescope, which allowed us to go and take really precise measurements of these distant objects once we discovered them. And we had things like this, charged couple devices. Now, everyone knows what a charged couple device is now because they're in your phones, they're in your video cameras, you use them all the time. But, back in 1995, you didn't use them. Astronomers used them, and we brought them from the military and sort of made them useful for a whole variety of purposes. And these digital detectors were 100 times better at taking pictures than photographic plates. And so although our telescopes got bigger, really these digital cameras were almost, or actually in many respects, more important. And so the ability to look and take these deep images over large parts of the sky were really a key ingredient. So When we look to the future, one of the reasons I'm here is because Carnegie and the Australian National University, as well as several other institutions around the country, are really looking to the future again to go through and to make a new telescope, a new technology to look even further in the past. And so just as we think new technology was the thing that allowed us to make our discovery, we expect new technology such as the world's largest telescope will enable that again. And so that's one of the reasons why I guess we're working so hard to make this happen. But these new telescopes are so big, you just can't do them by yourself. You need to go and have international partners. And so it's really important for me as an Australian to make sure that we work with our colleagues here to make this happen. And as I say, we've got 2 of our mirrors made now, but it's going to still take another 5 or 6 years to make the rest of them. So big is this telescope. So, oops. Since most of you haven't been to Chile, I thought I'd just do a quick travelogue of what it's like to go observing in the mountain. We used to share the mountain with our colleagues, and shown in silhouette is the opposition, as you should always have your opposition. Nick Sunsef is going here, and one of these telescopes, we would get 6 of these nights a year because, these are the only telescopes in the world, and we're sharing them world around. So as the sky went by, we would make sure that each image of each picture was exactly where it was supposed to be. All the data was perfectly constructed and behaving well. And then we'd take those images and we'd send them down to a bunch of people working on a bunch of computers, running software which I wrote but maybe wasn't so good, to find these needles in the haystack. Now we had to do this very quickly because supernovae explode and fade away quite quickly, and we need to now go, once we find one of these things, and take a spectrum and spread its light out with the biggest telescope on the planet, the Keck telescopes, and those are in Hawaii. So we had to turn these things all around within a few days. And here's Adam Rees and Alex Filipenko on Keck. And again, we're sharing with Saul because we're using the same telescopes, the biggest telescopes in the world. And so we used all these telescopes and Hubble Space Telescope together to go through and make our measurements. So, what was the answer? Well, here's our diagram. If we go through and look at this diagram, I measure how far back in time we're able to see. So here is 100 million years, so sort of dinosaur time, 8 billion years, so 3.5 billion years before the Earth was formed. Now these objects here, really if we look at our little trajectory, each object has uncertainty, and so that's represented by the bar. And you can see, on average, these objects here lie sort of, you can't really tell whether or not they lie in this part of the diagram or this part of the diagram. That's why we have to look a long ways away where that trajectory goes apart. And when we did this first data in 1997, we immediately noticed that these objects were all above this part of the diagram. The universe is not slowing down very much. It's not finite. It's not going to end sometime in the near future. I was very depressed because that's sort of what I wanted. But if we look at the yellow part of the diagram, we also notice that although some objects are consistent with the yellow part of the diagram, on average they're above that part of the diagram. So much on average that you need sort of 10,000 trials to find one that looked like this. And so that certainly made us interested in saying the universe seems to be speeding up over time. Now what we didn't know was that at the same time, while we were doing our work, Saul Perlmutter's team was finding the exact same result. So people often say, did you have a eureka moment? And the answer for me is, no, I didn't. Adam showed me that diagram the first time in Australia by email, and I said, Adam, you've made a mistake. Let's go through and track it down. So we tracked and tracked and tracked and tracked, and after a couple months, it was pretty clear there was no mistake. It was there. But the fact that the other team would have had to make the same mistake, I think, was quite powerful, because here were 2 teams that really had trouble agreeing on anything in public up to this date, suddenly agreeing on something crazy, that the universe is speeding up. So 2 papers came out, 1998 and 1999, and those are the papers that eventually led to Saul's team, the Supernova Cosmology project, and our team being awarded the Nobel Prize. So here we are, all dressed up in monkey suits in Stockholm, and since most of you and me don't really know what a Nobel Prize ceremony is like, I think it's worthwhile just having a quick look. So one of the things that you do is you get a driver with a car. Now, although it's a British TV show, I think some of you will at least appreciate the fact that my driver's name was Stig. And so for those of you who know that, you will probably understand that reference. If those of you don't, go look it up. So we got around very quickly in Stockholm. You get to meet the king, and he kind of mumbles some words to you. And in my case, I have given him a bottle of my wine. And so he thanked me up on stage for the bottle of wine that I'd given him. That's very nice. And in my case, you're also given a princess. So I got to escort the princess, and I pointed out, I said, geez, I look so glamorous with a princess on my arm. And that turned out not to be the best thing to say to my wife. She wasn't very impressed. She did get the prime ministers, though. So what is pushing on the universe? Well, it's been alluded to. The thing we have was Einstein's cosmological constant. That makes gravity push rather than pull. And we now typically call that dark energy. Now, if you go through a detailed analysis and figure out exactly that trajectory, what would give the trajectory we see, it turns out you need to have something which is essentially a mix of 30% of the universe being gravity that pulls and 70% of the universe being gravity that pushes. That's the mix that gives what we see. So people, when we made this measurement, were of course skeptical, as you would. When you go out and say, okay guys, not only did we miss 70% of the universe, but that stuff makes gravity push rather than pull, there's going to be skepticism. So people went out and did a lot of work. So 2 projects, one done in Australia, one done in the US, went through and did this census of gravity by doing together 1 million redshifts and 1 million individual measurements of galaxies. And that allowed them to judge how much gravity there was in the universe. When they did that measurement, they found that you needed about 27% of the amount of stuff to make the universe flat. You needed 27% of the universe to have gravitational attraction. That's the stuff they were measuring, the gravitational attraction. And you needed about 27% of the necessary to make the universe flat. Another experiment was also just to add up how much light there was in the universe. And when they did that, they realized there was only 4% of stuff that could be accounted for. The rest was dark. That is, for all the gravity we saw in the universe, which wasn't enough to make the universe flat, only 4% could be accounted for from what we could actually see in the universe. So we really had a double problem here. So you might ask, what's pulling on the universe? Well, we call that stuff dark matter, and we don't really know what it is today, but we have some good guesses. And one of our best guesses is that there's some class of particles that we haven't yet managed to discover that are not dissimilar from a neutrino, and a neutrino will go right through the Earth, given a chance. And it might be that these things are bigger than neutrinos, or there's just a lot more of them, but that they also would go right through the Earth. And so something like that could still have evaded our detection. It would have gravity just like atoms, but is essentially invisible because it doesn't emit light, it doesn't form stars or anything. Now the other key thing we had was a measurement of the cosmic microwave background. So the cosmic microwave background is this image of the universe, and what we see here are essentially sound waves sloshing around in the universe 13.7 billion years ago. So that measurements, the first sloshing was made by a large team who is represented by John Mather here today. So he's here, so it's great to have him. And that was awarded a Nobel Prize not too long ago as well. And so this is one of the great tools we have in astronomy, is looking at the sloshing of sound waves in the early universe, because we can make incredibly precise measurements of the universe because we know from physics to about 0.1% how these sound waves, what the size of these sound waves are. And so by comparing that to what we see, it turns out you can measure the geometry of space itself. And so starting in about 2000, experiments went which enabled us to compare a universe that has geometry which is like a saddle, and those sound waves will look very small in the sky, to ones where the universe is finite, and those objects will the sound waves will appear very big. What we found was, well, right in the middle, that the universe is within 1% of being geometrically flat. That is saying that if you add up everything in the universe together, and it turns out anything will do here, it doesn't have to, anything that's matter, anything that either pulls or pushes gravity, anything that involves gravity at all, well, that counts towards this. And so that allows us to do some cosmic subtraction, where all matter is 100%. The stuff that's that pulls, a gravitationally attractive 27%, and that sort of leaves us with mystery matter, 73%. Now that 73% is very similar to, of course, the 70-30 mix that I told about. So you put it all together, we have a really messy universe, which seems to be 4% atoms, the stuff we're made out of, 22% dark matter, 24% dark matter, depending on the day, and dark energy, this stuff which makes gravity push rather than pull, 72%. And so it's a crazy universe, but it is one that makes very precise predictions that we can go out and test. So dark matter, it turns out, as the universe expands, the amount of dark matter in atoms stays the same. The universe gets bigger or the universe gets smaller, you don't make or destroy this stuff. On the other hand, dark energy is part of space itself. So as space gets bigger, or if we look back in time when space is smaller, then the amount of atoms and gravity to this stuff that's pushing on the universe will change. Graphically, you can think of it this way. Go through and look at the universe. As the box gets smaller, when we look in the past, the density, amount of stuff in the box per volume increases. The amount of stuff, dark energy, that's part of the box itself, well, that doesn't change. And so you end up with, as you look back in time, more and more gravity attraction compared to gravity pushing. So that provides an interesting test of testing dark matter versus dark energy back in time. And so using the Hubble Space Telescope, and a project led by a whole bunch of people, but initially Ron Gilliland and Mark Phillips, they were able to find an object in one of the deepest images ever taken of the sky. And in this area, there was a star, which doesn't look like much. It's right there. It's a little smudge, but it is the most distant exploding star of this type we've ever found. And that object allowed us to look about 9 billion years into the past. Now, Adam Rees, who is still at Johns Hopkins and Space Telescope, was able to use the Hubble Space Telescope to do this again and again and again, and make really precise measurements of what was going back a long time ago, far enough back when the universe was small enough that dark energy would not have been in charge of the universe and causing it to speed up. So he was able to look back when the space was 15 times smaller than it is now. And what he found was that, just as predicted, the universe went from speeding up, and then it changed directions and started slowing down, just like we predicted when we made this measurement. So that was a great thing to help show that something like dark energy is at play. Now, one of the things I like to do is to speculate, and speculating about the future of the universe, which was my initial goal, unfortunately now is a bit of a speculation. And that's because we don't really understand dark energy. The future of the universe looks like it's going to be dark energy. The big question we're trying to grapple with here in physics today is, does dark energy get created exactly with space, like Einstein suggests, or a bit faster or a bit slower? And that's one of the big questions. So imagine it's Einstein's dark energy. It's the cosmological constant. It gets created exactly as space gets created. Well, dark energy has won the battle of the universe, and it will continue to accelerate the cosmos forever and ever, faster and faster. Eventually, the creation of space will happen so fast that light from objects we can see now will not be able to reach us. Space between us will be created so fast that the light will get stranded. Galaxies we see now will become invisible in the future. Already, the galaxies I've shown you, from those deepest pictures of space, the light those galaxies are emitting right now will never reach us because the universe is speeding up. When I go and put in my space telescope proposals, I always like to remind people that we need to do our cosmology now, because in the future I'm not going to have the opportunity. There ain't going to be anything to look at. But until we understand dark energy, we really have to contend with anything as possible. Dark energy can change in the future and slow the universe or speed it up. It can even make the universe accelerate faster than Einstein's dark energy, the cosmological constant. And this leads to the idea of the Big Rip, which I think is possibly the most exciting way for the universe to end. If dark energy gets created a little faster than space gets created, then it turns out that this room, where this room is not expanding right now, gravity, because there's a lot of it here, has collapsed this room a long time ago, and there's dark energy isn't doing anything here. And if we have Einstein's cosmological constant, we're safe. But if we have this stuff that gets created faster, then this dark energy can start eating into the parts of space that have already collapsed. And the outcome of this universe is that eventually, every piece of the universe, down to the subatomic level, will be taken infinite distance apart. And that all happens at the end very quickly. You will literally be able to go out one day and watch the sun disappear just after the stars had disappeared. Now, you don't need to worry. You don't need to worry too much. This is probably not going to happen for at least 30 to 50 billion years in the future, and probably more like 300 to trillion years in the future. So it's not going to happen anytime soon. But it is a possible ending to the universe, and certainly leaving what I think is really nothing. That is, when everything is broken down to the barest possible thing and separated from an infinite distance. That is an exciting ending. Either way, it's the one I like anyway. Either way, I think we can look is that unless the dark energy goes away, the universe will, at an ever-increasing rate, expand and slowly fade away before our eyes. And I'll stop there. Thank you very much. Thank you.
Dr. Schmidt has obviously provided us with a fascinating tour. We do have the opportunity for a few questions. There are microphones in the center aisles, and I invite those who would like to raise some questions with Dr. Schmidt to come to them. Please.
Good speaker. I am impressed.
Thank you.
And you mentioned one of my heroes, Slipher. How do you say that?
Well, I'm probably not an expert,
S-L-I-P-H.
but I call him Slifer, but I've heard
Yeah,
Sleeper
that's
as well.
fine. He's a genius. I want you to know.
He was a great guy.
If you didn't know that, your professor, Kishner,
Yes?
I read his articles. I did research on my own. And Slipher observed 41 galaxies. 36, he thought they were going away from us.
Yes.
5 of them, they're coming towards us, or they are standstill. He doesn't know. That's in his paper.
Yep.
So that is a benchmark research he has done.
Yep.
Now, if you go back and read that carefully, I'll be delighted to work with you and show you your gut feelings in the beginning when you started this you want to solve it, that were right.
Okay.
And then, why I'm saying that right? Chadwick, in 1930, he showed us in an atom there are 3 parts. One is, of course, a neutron, and proton, and electron. In the same way, if you put a neutron, or each and every galaxy you are talking about, they are going around a neutron. So when you observe them when they are going away from you, you see them going. When you observe the other way, coming down to you, you see they are coming towards you. Universe is not expanding, dear sir. Respectfully, I submit that to you.
Okay. Thank you very much.
If you want to read
the beautiful thing is I'm an experimentalist, and you're clearly a theorist, and so I can test your results, and that's how I like to work.
Yeah, I wondered if I'm not sure if you can give us an intelligible answer, but I wonder why you described the cosmic background radiation as being sound waves sloshing around.
All right. So when the universe was born, for some reason, soon after, there was imposed on it by, we're not really sure why, but we like to call it inflation, is the theory. And it would seem that there were essentially what we call perturbations, but we can call bumps and wiggles. There were sort of little places where there was more matter and less matter around. Now the universe is like a giant pool. It was made up of hydrogen and helium. And where there was more mass, well, that part started to collapse a little bit. But then when it collapsed, it heats up a bit. And so that heating up, that pressure, creates a sound wave. Pressure travels by sound rather than by light. And so you ended up with these parts of space kind of doing accordions back and forth. And so you ended up with this whole range of sound waves doing accordions. Now, it turns out there's sound waves on all sorts of scales, and what you end up with is a big sloshing mess, which turns out really hard to, you can see what it looks like, and it turns out when you go through and measure it the way we would measure it, which is how many sound waves are there at different wavelengths, we can make these exquisite predictions because although it looks like a mess, physically it's beautifully it's a beautiful system. It just looks like a perfect little chamber where you can go through and put a little bunch of little splashes and measure things perfectly. And so, as I said, John Mather here in the audience is the real expert since he has a Nobel Prize in this.
Other microphone.
Good evening, Dr. Schmidt. I have two questions. The first one is, if the universe is expanding, is our galaxy or our solar system expanding within itself? And my second question is, when you look at light from outer space, how do you know whether the light is from 10 billion years away from us or 5 billion years away from us?
Okay, so the first question is that our own solar system, our own galaxy, our part of the universe is not expanding anymore. It was expanding a long time ago, but there was so much gravity that our gravity stopped the expansion, caused our little part of the universe to go in reverse and do a crunch, and form planets and stars and galaxies. That's why we could exist. All right, so it's only on distances of about 20 million light years where the universe really starts to expand smoothly and where our part of the universe hasn't collapsed down. In terms of light, the way we do it is we measure how bright objects are. And so I will look at one of those exploding stars, which is 5 billion suns worth of star, or a 10 with 43 zeros behind it watts. So it's a big light bulb. And I see how bright it is now, and I can see the further away it is, the fainter that light bulb is. And because I know how many watts that light bulb is, I can measure its distance. And so these objects are very, very faint. They're 1 billion times fainter than I can see with my eye. But I just told you that there are 10 with 43 zero-watt light bulbs. That's a really bright light bulb. And that tells me that they're 8 or 9 billion years into the past, or 8 or 9 billion light years in distance.
Just a follow-up.
Please,
How do you know?
we have a lot of people to ask questions.
Okay, sorry.
Please.
Professor Schmidt, the theories that you and your colleagues have propounded suggest that the universe is flat rather than curved, and that the furthest galaxies could be rushing away from us so quickly that their light will never reach us, suggesting they're traveling at faster than the speed of light. Don't those two propositions overthrow the theories of Einstein?
Turns out they don't, because as I tried to allude to, that with Einstein's theory of general relativity, space itself is created. So those objects are not moving away from us. Rather, space is being created between us. And so that when you have that space being created, as light travels through it, that space can get created faster than light can make it through. And so it turns out it does not violate the idea that things travel faster than the speed of light. They're not traveling faster than the speed of light. It's just the space between us is being created.
Please.
Good evening, Dr. Schmidt. I've been reading your papers from the beginning, and one thing I notice is when you plot them, you plot the redshift and the distance, I forget the word. Anyhow, I like to see it the other way with the diameter of the universe versus time.
Ah, okay, yes.
So I took the same data you have, And I actually did that computation, and I got a really ugly curve. Some of the supernovas, the older supernovas were older than before the Big Bang. And I said, what am I doing wrong?
Okay.
And I said, I looked at all my assumptions, and one assumption that might be suspect is that the universe is flat. So I said, I'm going to put some curvature in there. And when I put the curvature in there, I got a beautiful picture. And the curvature was about 4 billion light years negative, imaginary. Yep. I sent you an email, but I don't think it got through.
I'm sorry, I've got about 20,000 of them, unfortunately, so I'm a little behind. So there are other ways. The way we have described the universe is the way that I think at present is the simplest way to look at the data. It is the way which, as far as I know, does not have any observational problems. That is, the model we have provided is self-consistent with Einstein's equations, and it can be used to calculate everything we can observe correctly. Now, that does not mean that it's the only way to do it, and obviously I'm not too familiar with what you have done, but I think me and my colleagues are certainly open to new ways to look at the data, and so, you know, there are many people looking at that, and so if there are new theories that can predict everything we see in the universe, I promise you they will rise and be tested, and if they stand the test of time, they will be accepted, and so that's the challenge.
Please.
Yes. You mentioned what I think is called the principle of homogeneity. That is to say that anybody anywhere in the universe is going to see basically the same thing. It's a principle that suggests there's no such thing as the edge of the universe. And then from the cosmic microwave background, you have the finding that the universe is basically flat, which sounds very Euclidean to me.
Yeah.
Okay, like it's just like this room.
Yep.
Right, and that we can envision it expanding as if this room was expanding, but the room, of course, does have an edge.
Yep.
I assume there's no real contradiction here, and perhaps it needs some mathematical hocus pocus to...
Well, it doesn't even need much. It's Euclidean. If you think about something that is flat, this room has an edge. It's not Euclidean on the edge anymore. So imagine pure things going out in all directions. They go out to infinity. So if things don't bend, imagine the Earth, okay? The Earth is finite because it bends onto itself. But if the Earth were flat, it would either have an edge where the Euclidean ends, or if the Euclidean goes, it would be infinite. Now, the universe we live in, we think, is infinite, or as close to infinite as we can tell. And so that when it expands, infinity gets bigger. That's like taking 2 times infinity. And of course, when you take 2 times infinity, you get infinity. And that's sort of our universe. It's infinite, you make it bigger, it's still infinite. And that turns out to be perfectly reasonable. Maybe you'll have to trust me.
Okay, we're going to allow the people who are at the microphones now to ask their questions, and that will then call this an end. Please.
All right, Dr. Schmidt. I don't want to seem sensationalist, and even though CERN did say it had a mechanical error that could have caused neutrinos to go faster than they actually are, if they do go quicker than the speed of light, how does that affect your work, and does it play a role in explaining dark energy and how the universe accelerates quicker?
So the faster than speed of light neutrinos, which appears to have been traced down, I was extremely excited by, because although I thought it was probably wrong, if it were right, it would be such a major change to the way we think about the universe that it would cause nothing but excitement in physics for the next decade. So we had no idea, no one really had a reasonable way to make this happen, hence why people were so, I think, skeptical about the result. So I have no idea how it would have affected our result. As I said, we have tested our result many, many ways, and it keeps on able to explain what we see. And because of that, we think it's at least close to the mark. But who knows, maybe that happening would have had the opportunity to explain why the dark energy is there in the first place or something like that. We don't know. But I'm afraid it looks like it was too good to be true and it's not going to be around anymore. I was very depressed.
Please.
I like it. I like excitement.
Dr. Schmidt, first, thank you for a fascinating evening. A simple question. You described the discovery that the universe is expanding at an accelerating rate. So could you talk about what that implies about the conservation of energy, and if energy is not conserved on a universal basis, from whence might be coming that energy?
Okay. So the idea of conservation of energy, as most people think of it, does not really work under general relativity. It doesn't mean general relativity is wrong. It means that general relativity conserves something bigger than energy, and it conserves something we call the stress momentum tensor. And so what happens is there's a lot of philosophy discussed within the field of this, but effectively the acceleration is able to, when the universe is accelerating, it's flattening space. And so the dark energy is actually being traded off in the flatness of space. And it turns out that all adds up when you use general relativity. So it's not that somehow we're getting something for nothing. It turns out there is a penalty to be paid, and that's what we're doing to space, and so it adds up. It's not energy in the normal sense, but it is something equivalent to it within Einstein's language. And so it's just that energy is, within general relativity, not exactly the right thing you want to talk about. But you're not going to suddenly make perpetual motion machines. We can't do that. You do have to conserve something.
Hi, just a follow-up question from earlier, the answer that you gave me. So you mentioned that you know the light bulb to be certain wattage. How do you know? Is it by the mass of that light bulb?
So in this case, what we do is we appeal to the work of Wendy Friedman here in the second row, and she's gone through and done a series of geometric experiments. The first one we do is we measure the distance to the nearest stars by seeing when the Earth's on this side of the sun, and then we go to it's on the other side of the sun, the position of the stars move a little bit because it's perspective. It's just like switching your eyes to your finger. And then we go and we kind of move that out and out and out till eventually we're able to calibrate how many watts these stars are that we see. So it's a big, long, drawn-out process, but it effectively starts with that first geometrical measurement. And that, of course, assumes we know the distance to the sun, and it turns out we can use radar to do that, to about a centimeter.
Thank you.
Okay, our last question.
How do you detect sound coming from such enormous distances?
So we don't detect sound. So in terms of the cosmic microwave background, what we see is the sound waves are going back and forth. And so when the sound compresses, it makes the matter more dense. When the matter is more dense, then there's several effects that end up changing the temperature of what the universe was at that time. So that map is actually looking at the universe. It's about 2.7 degrees Kelvin, or minus 270 degrees Celsius. Can't even do it in Fahrenheit, I'm sorry. I've been in Australia too long. So those little different colors are actually representing different temperatures of the universe back then. And those temperatures tell you where the sound waves are.
Thank you.
Yeah.
Dr. Schmidt has provided us with an absolutely fascinating evening. Please join me in thanking him.